On the night of February 24th, 2026, an observatory perched on a Chilean mountain sent astronomers 800,000 separate warnings before sunrise. New asteroids, stars exploding, supermassive black holes flaring, and that flood was generated before the machine's real mission had even officially begun. When the 10-year survey finally switched on a few months later, the number of nightly warnings was projected to climb into the millions. But here's the part almost nobody online is talking about yet. The truly revolutionary thing about this telescope isn't its mirror, its camera, or any single picture it takes. It's something stranger. Stay with me, because by the end of this video, you'll understand why astronomers are calling it the greatest movie ever made, and why what it has already found in our own solar system might quietly rewrite the map of our cosmic neighborhood. Let's start with the basics, because you need to know what this machine actually is before the numbers mean anything. This is the Vera C. Rubin Observatory, sitting on top of a mountain called Cerro Perched in the Chilean Andes, one of the driest, darkest stretches of sky on the planet. No clouds, no city glow, no moisture hanging in the air to blur the stars. Astronomers didn't get lucky with this location. They chose it on purpose. The main mirror is 8.4 meters wide. Attached to it is the largest digital camera human beings have ever built, carrying 3,200 megapixels. Think about that for a second. The phone in your pocket probably carries somewhere between 12 and 50 megapixels. The single camera carries 3,200. If you wanted to display one full resolution image from it, you would need roughly 400 4K television screens lined up side by side. The camera itself was constructed at SLAC National Accelerator Laboratory in the United States, is roughly the size of a small car, and weighs about 3,000 kilograms. It operates with such precision that the tiniest vibration would ruin an exposure. Inside it sit 6 large optical filters, each tuned to capture a different band of light, from near ultraviolet all the way through to near infrared, letting scientists study everything from hot young stars to faint, distant galaxies in a single coordinated survey. And every image has to pass through layers of calibration, checking focus, checking exposure, checking alignment before it joins the official dataset. That's why the commissioning phase took as long as it did. A mistake at this stage would ripple through 10 years of observations, and once the decade-long clock starts, there's no going back to fix small errors. But size isn't the story. Speed is. Older great telescopes work like careful portrait photographers. They pick one target, stare at it for hours, and move on. Rubin works like a security camera for the entire southern sky. Roughly every 40 seconds, it captures a brand new, incredibly detailed image, then swings to the next patch of darkness and does it again, 40 seconds. About 1,000 images a night, every night, for 10 years straight. And that cadence changes what astronomy even is. Stitch those repeated images together and you don't get a picture of the universe, you get a movie. A real, observed, honest-to-goodness film of the night sky changing over time, made from actual observations. Not animation, not simulation. The official mission carrying this out is called the Legacy Survey of Space and Time, or LSST. And its plan is to scan the entire southern sky over and over roughly every 3 days for a full decade. Here's why that repetition matters more than the resolution. The universe is not a still photograph. Stars explode, asteroids drift, black holes flare and fade. A supernova brightens quickly and dims over days or weeks, and if no telescope happens to be looking at that exact patch of sky at that exact moment, the event is simply missed. Older surveys missed enormous numbers of these events, not because their instruments were bad, but because they looked slowly and rarely. Rubin solves that by never really looking away. Revisit the same sky every few days, and every explosion, every flare, every fading afterglow gets caught somewhere in the cycle. Scientists on the project have called the result the greatest cosmic movie ever made. And on June 30th, 2026, that movie officially started rolling. But before we get to what the telescope has already found, it helps to understand the woman whose name it carries, because this observatory exists, in many ways, to finish work she began decades ago. Vera Rubin was an American astronomer who studied how galaxies rotate, and she noticed something that shouldn't have been possible. The outer edges of galaxies were spinning almost as fast as the inner regions. Based on the visible matter alone, the stars, the gas, the dust you can actually photograph, the outer stars should have been moving far more slowly, the same way distant planets crawl around the sun compared to the ones close in. Something invisible had to be out there, adding extra gravity, holding those galaxies together from the outside in. Her careful, patient measurements became some of the strongest evidence scientists ever gathered for dark matter. A mysterious substance that gives off no light, can't be seen directly, and yet appears to make up roughly a quarter of everything in the universe. Rubin spent her entire career being precise, being patient, and trusting what the numbers told her, even when the community took decades to fully absorb it. So when the National Science Foundation and the Department of Energy built the most advanced survey telescope in history, they named it after her. It fits, because this machine is, at its heart, a continuation of her method. Watch the sky relentlessly, measure it honestly, and let the patterns reveal what can't be seen directly. Its two biggest targets are her legacy, dark matter, and its stranger partner, dark energy, the mysterious force that appears to be pushing the universe's expansion faster and faster. Now the timeline, because the dates and numbers here are genuinely staggering. On June 23, 2025, the team held a public event called First Look, and the world saw the telescope's first real images. One of them was a composite of two glowing clouds of gas and dust, the Trifid Nebula and the Lagoon Nebula, built from 678 separate exposures, captured across roughly 7 hours of observing time. In total, that single image contained about 2 trillion pixels of data, with enough detail to keep zooming in and finding stars hidden inside dust that older telescopes simply couldn't resolve. Another frame released the same day showed the Virgo cluster, countless galaxies scattered quietly behind bright foreground stars of our own Milky Way. Then came the early test data, and this is where even the people who built the machine were stunned. In just over 10 hours of test observations, before the real survey had officially begun, Rubin had already captured millions of galaxies and Milky Way stars, and thousands of asteroids inside our own solar system. 10 hours. Most observatories take years to build a catalog like that. Rubin did it in less than half a day. And during the early optimization surveys that followed, astronomers used about 6 weeks of test data to discover more than 11,000 brand new asteroids, one of the largest single batches ever submitted to the International Astronomical Union's Minor Planet Center. Inside that group were 33 previously unknown near-Earth objects. None of them pose any danger to Earth, but tracking near-Earth objects remains one of the most important jobs any observatory can do. The same early data revealed 380 new trans-Neptunian objects, icy bodies orbiting far beyond Neptune, 2 of them on orbits so stretched they carry them nearly 1,000 times the Earth-Sun distance away from the Sun. Orbits like those are exactly the evidence researchers would use to test the long-debated idea of a hidden ninth planet, 5 to 10 times Earth's mass, possibly warping the paths of distant outer solar system objects. Even if Rubin never photographs that planet directly, finding more warped orbits would be a genuine clue pointing toward its existence. On top of all that, the early data sharpened the known orbits of more than 80,000 previously tracked asteroids, making our map of the solar system more precise than it has ever been. Then, in January 2026, the first peer-reviewed scientific paper based on LSST camera data was published, and it contained a record. The fastest spinning asteroid larger than 500 meters ever documented, sitting quietly in the main asteroid belt, an object researchers say simply could not have been detected without Rubin's unique speed and sensitivity. And that brings us back to the night of February 24th, 2026, 800,000 alerts in a single evening, the true beginning of the public alert stream. A few months later, on June 30th, 2026, after years of construction, testing, and careful operational review, the 10-year legacy survey of space and time officially began. From that night forward, Rubin began collecting close to 20 terabytes of data every single night, and across the full decade it is expected to generate roughly half an exabyte of information, an amount so enormous that the first year alone will outweigh everything every other optical observatory on Earth has ever collected combined. Not close to it, more than all of them put together. At full operating speed, the system is expected to issue millions of alerts per night, with some estimates running as high as 10 million. Each one represents a real change happening somewhere in the sky. An asteroid shifting position, a star exploding, a black hole flaring, a galaxy changing brightness. No group of human astronomers could ever read 10 million nightly notifications on their own. So the pipeline is built around artificial intelligence and machine learning systems, designed to filter the noise in real time and flag the events that matter most, allowing researchers around the world to react within minutes and turn other telescopes toward whatever Rubin just detected while the event is still happening. This is part of what scientists call multi-messenger astronomy, studying the universe with multiple types of signals at once, light, gravitational waves, and cosmic rays working together, one observatory acting like a smoke detector for the entire southern sky and dozens of others racing to respond the moment the alarm goes off. All of that raw data doesn't sit on a hard drive in Chile. It travels to United States data facilities hosted at SLAC, where it becomes available to the wider scientific community, including groups like the Dark Energy Science Collaboration, researchers spread across the globe using Rubin's observations to measure how fast the universe is expanding and how matter is distributed across the cosmos. And crucially, this data will not be locked behind closed doors. For the first time, this much astronomical information will be available to this many people at once, major institutions, small universities, and eventually even members of the public getting hands-on access to a universe of information that used to belong only to astronomers with time on the world's biggest telescopes. Phil Marshall, the deputy director of Rubin operations at SLAC, described the journey plainly. It took 20 years of hard science, engineering, and determination to reach the point where the team could finally call action on what he described as a blockbuster movie of the universe, and the millions of alerts generated in the first months alone proved the machine works exactly as intended. A genuine discovery machine finally switched on. It's worth being precise and fair here about what this does and doesn't mean, because that honesty is exactly where the real story sits. An alert is not a discovery by itself. It's a flag that something changed. And the overwhelming majority of those flags are routine, known asteroids moving as expected, variable stars pulsing on schedule. The 800,000 alert night was a milestone of capability, not a night of 800,000 breakthroughs. And the most tantalizing threads in the early data remain exactly that, threads. The warped trans-Neptunian orbits are evidence that could support a hidden ninth planet, but they don't confirm one, and researchers are careful to say so. The survey's biggest goals, real answers about dark matter and dark energy, are decade-long questions, and nobody serious is promising they'll be settled quickly. But that calibration isn't a reason to be less excited. It's a reason to be more excited, because the underlying capability is real, measured, and already demonstrated. A telescope that finds 11,000 new asteroids in 6 weeks of test data is not a promise. It's a track record. Over the full 10 years, our researchers expect Rubin to catalog roughly 20 billion galaxies, triple the number of known asteroids, and multiply the identified trans-Neptunian objects by close to 10 times what we currently know. Every one of those detections adds a piece to the puzzle of how the solar system formed and how the universe's structure evolved. Mike Brown, the Caltech planetary scientist who has watched this project develop for more than 2 decades, has pointed out something worth sitting with. Ask 50 different astronomers what they're most excited to find with this telescope, and you'll likely get 50 completely different answers. That's how rare it is for one instrument to touch nearly every corner of a science at once. Think about everything this single machine is doing simultaneously, mapping the solar system in more detail than ever recorded, catching supernovae in the act, tracking supermassive black holes flickering across billions of light years, building toward a catalog of 20 billion galaxies, and underneath all of it, quietly gathering the exact kind of data that could finally crack the 2 biggest mysteries in modern physics, the same 2 mysteries that gave this telescope its name. And we are still in the earliest days. Everything described so far, the 11,000 asteroids, the record-breaking spinning rock, the 800,000 alerts, the 2 trillion pixel nebula, happened before the real survey had fully begun. The 10-year clock only started ticking on June 30th, 2026. Somewhere in that nightly flood of images, there is a very real chance Rubin captures something nobody predicted, simply because it is watching the sky more closely, more often, and in more detail than any instrument in the history of astronomy. If you want to understand what's really happening in astronomy instead of just the hype version of it, that's exactly the kind of grounded breakdown worth subscribing for, because we'll be covering this observatory's biggest updates across the next 10 years. And drop a comment telling me which part stopped you. The 2 trillion pixel nebula, the fastest spinning asteroid ever found, the 800,000 alerts in a single night, or the fact that this telescope never really looks away. That tells me exactly which stories to break down next. We'll keep tracking how the story develops as new research comes in. Thank you for watching, and I'll see you in the next one.